Okay, so let's pick up where we left off and talk about correlation and causation, and under which circumstances we may see correlation become equal to causation. So, obviously, it's a famous saying that correlation is not causation, but under some circumstances, we could uh, take correlation, that is an observable data point, and we could argue that that correlation is causation, that relation we are seeing between these two variables is happening because one is causing the other. So this is what we are most interested in. We are in policy analysis, we are interested in some amount of causal effect of one variable on the other, right? So let's begin by refreshing some important points. So firstly, we are randomizing. So when we are randomizing, the main thing is that the potential outcomes are independent of treatment assignment. So this is important. And there is also the common support assumption, which is that the probability of being assigned treatment has to be a value between 0 and 1. Okay, then there were some proofs and some results we got from the previous analysis, and also there's some two properties. The first property was that ATT is equal to ATE, and under these assumptions, the second property was that there is no selection bias anymore. And the third property, or the third thing we inferred, was that simply because this is true, need not be that the observed value is also independent of treatment assignment. So these are the main inferences we had in the previous few videos. So now we will go into how correlation and ATE might be related and how it can be proportional. So consider the covariance of yi di. Let's write this as expectation. Okay, so in expectation form, how may we write this? So there is a formula for this actually in expectation. So let me write the more generic formula first. So the covariance between, this is no longer, I'm not discussing causal inferencing or RCT anymore. I'm refreshing a formula of covariance that relates to its expectation. So the covariance of x comma y is equal to expectation of x minus expectation of x whole bracket times y minus expectation of y. This is a formula you can remember and write. So now let's rewrite this formula in terms of our variables of interest. So that's expectation of yi minus expectation of yi whole brackets times di minus expectation of di. Oh, glitching today. Yeah. So let's expand this. I can write this as expectation of, I'm just multiplying it term by term, yi di minus yi expectation of di minus di expectation of yi and plus expectation of yi di. Okay, now let's see what we can reduce in this. Obviously we can now sort of put the expectations inside. So this is expectation of yi di minus expectation of yi expectation of di, okay, minus expectation of di. I'm just sort of this outside expectation I'm taking inside, that's what I'm doing. Expectation of yi plus expectation of yi times expectation of di. Now obviously some of you might have a question that when I took this expectation inside to a term like this, why didn't I write it this way? Well, because if expectation of the expectation of a variable is going to be equal to the expectation of that variable, that this is a property, and that's why this term is just directly equal to this. So that's why I don't need to write the double expectation anymore. And this is true because this term is just a constant and the expectation of a constant is just the same constant, so that's mainly why. So getting back to our equation, so this is the massive equation we have, but neatly two things cancel each other out. So we have expectation of yi di minus expectation of yi times expectation of di. So the covariance, the covariance of yi comma di is this whole thing. Okay, so how do we further proceed and relate this to ATT or ATE? We know from a previous result that this term here can be written as expectation of yi of 1 times expectation of di minus expectation of yi. Sorry, I mean that this term can be written as this. Do you remember this first term? And now I'm just copying the second term down. If you don't remember, try to recollect, but mainly we are just using this proof where we try to understand if yi and di are independent, and we concluded that expectation of yi and di should be equal to this whole term. So this was the whole proof for it. You can go back and look into that, but this is our final sort of formula we have. Now that we have this, we can take expectation of di outside the bracket and we can write it as expectation of the potential outcomes minus expectation of the observed outcome times expectation of di. Okay, now let's do something to the first term. What may we do now that we have done a couple of proofs? What do you think we can do? What term here may be expandable? So obviously we are going to, as always, write the observed outcome, which is yi here, as a function of the potential outcomes. So let's do just that. The second term can be written this way. So expectation of yi of 1 minus expectation of yi of 1 di plus 1 minus di times yi of 0. Okay, so also this is whole times expectation of di. Okay, now what may we do? Let's further simplify the things inside this bracket. So what we may do is, let's take this expectation out and make this a whole expectation so that we can write this quite easier. So expectation of yi of 1 minus yi of 1 times di plus, now that this minus sign has gone inside, it should be minus 1 minus di times y of 0, and of course still whole multiplied by expectation of di. Yeah, now how may we proceed here? So here obviously again I can take yi of 1 outside I think we need to add stretching sessions in between such proofs. Yeah, but it's coming neatly now. It's going to be elegant in a bit. Okay, now I can take 1 minus di outside. So it can be expectation of yi of 1 minus yi of 0 times expectation of 1 minus di times expectation of di. Okay. Now what is our final conclusion? This whole term is equal to the covariance of yi comma di. Do you notice some patterns? Yes, we do. We are smart students. And this one is nothing but the average treatment effect. And this term I can write as expectation of di minus di squared. And of course, again, smarty brains, this is ATE and this is nothing but variance of the dummy variable di. Okay, so the covariance, finally we have that the covariance of yi di is equal to the ATE times variance of di. So which means that ATE is equal to covariance of yi di by variance of di. So in this particular scenario, given all these assumptions, ATE, which is a causal estimate, becomes equal to the correlational estimate that we get from our regression equations. That's the main conclusion of this video. So we will then in next video cover how this works out in a regression equation and how we will actually observe this in data.